like to welcome all of you to our special session here. I would like to thank CAL-TEK for organizing this special session. The session is dedicated to the 5G era Horizon 2020 project, which is 5G Enhanced Robot Autonomy. In this session, we will have 5 presentations coming from the partners of the consortium of 5G era. We will start with Robotnik on 5G era. They are the coordinators of the project, so they will present the general idea and description of the project. And this will be presented by Alessandro di Fava, if I'm pronouncing this right. I'm not sure.
Yes, you did right.
Excellent.
Hello.
So, hi, Alessandro. Please, you can take on the stand.
Okay, let me share my screen. Hello to everybody. Thanks, Marius. Can you see my screen?
Yes, we do.
Okay, so as Marius said, here, I mean, we are the Robotic, the coordinator of the project. Let me give an overview before that all the technical details will be discussed later by my colleagues. And so 5G era, it's a project, a European project about 5G, and more specifically is about how to improve the robot autonomy using the 5G. And we will see a little bit an overview of the project and the consortium, and why, I mean, the goals, the challenges, the objective behind this project, and also how we will showcase the project with a brief overview of the use cases that they will go on during the project. And I mean, to say something about where started the project, I mean, this project is part of a program, the Horizon 2020 program of the last 3 years. And especially the call comes from the ICT 41 of 2020 of last year, where the goal of this call was about 5G innovation for vertical with the third-party services. And indeed, this 5G era project aims to take advantage of the 5G technology to assess the challenges in robot autonomy, to bring some advances of the usage of the 5G to find solution improvements inside the robot autonomy. Because as we know, I mean, robot autonomy is a big challenge. Can cover different sectors like automated mobility, healthcare, transport, and manufacturing. And from one side, because we cannot, I mean, we cannot put all the services directly inside the robot, because this will require a big computational effort. But from the other side, also, we need, when the robot works in this complex environment, it has to communicate with the environment, with a remote host, or also among robots. So the computational power, the communication are very important goals that with 5G we hope to bring some improvements in these goals. The overall budget of the project was about 6 million. Is about 6 million, and the project just started this year. So we are currently in the month 9 of the project, and the project will take 3 years. Just to have a brief overview of the people involved in the project. Okay, us, Robotic, we are the coordinator. We are located in Spain and Valencia. And in the consortium, there are 8 SME companies, 3 research developers center, and 2 industrial partners. This to give you an idea that this is not a research project. This is an innovation action. This means that the end goal is very toward the market, toward to bring a real effort, a real benefit on the robotic side. And indeed, the main goals of the project is to use to take a user-centric paradigm to try to integrate vertical knowledge inside the existing standardized 5G framework, using this to improve quality of experience of the 5G enhanced autonomous robot, and obviously minimizing the robot developers, because when you want to use 5G inside a robotic system, this comes with a lot of effort that you need to bring all the 5G infrastructure inside the robotic system. And so we also want to bring some services and APIs to put this effort as minimal as possible. And the key challenge behind this are mainly three. One is to optimize the quality of experience of the 5G orchestration for vertical application. This will come with the intent recognition and end-to-end interpretability of the proper orchestration system, because this can lead to possible creation of ineffective control policies. So we have to try to overcome this problem. The other challenge is about the scalability and availability of and the future velocity of the system, that we try to optimize this using a cloud-native approach to use 5G facilities to adapt them to cloud-native approach for efficient service delivery of the robot framework. And the third challenge, as I said before, is to create and extend, to create some APIs to extend the 5G environment for more robotic vertical sector, so with some more robotic services, more oriented to robotic services that nowadays are not available in 5G environment. So to try to also engage all the players, especially from robotic platform developers, to bring them toward closer to end users. And to sum up, the objectives of the project is to use an intent-based networking paradigm to optimize the quality of experience, to try to improve the robot autonomy in a real-world application, to have a 5G middleware to enable cloud-native resource provision of autonomous robots. Also to create some APIs by integrating the ROS, the Robotic Operating System, with OSM. And this because nowadays the majority of the robots, they use ROS for their development. So bringing this in APIs together with 5G maybe will facilitate and make closer the robotic to the end user, to the 5G providers. And obviously to showcase all of this in some vertical application, some real experiments to try to improve the quality of experience. And said this, we choose the 4 use cases to try to showcase this approach. Also, this taking into account, as I said in the beginning, all the some complex and industrial sector where the robots currently work. We have a first use case that is about inspection robots in some public areas to protection and disaster relief. And here we will try to use our Robotnik platform. Here in the image, you can see the Summit XL. Or a second use case will be about semi-autonomous transport. Here in the image, you can see the delivery robot from Bring Auto, to try to also to overcome the communication and the orchestration of the robot with the 5G. A third use case that we will explore and exploit will be robots inside healthcare, where the RB1 robotic robot will use to carry on a cart around the hospital, also thanks to try to improve the communication and the effort of the robot, the orchestration with the 5G. And the last one will be a bracing robot inside the manufacturing areas to try to remote have a monitoring of the robot, also to try to have a a closed loop control of the robot using the 5G infrastructure. And mainly, more or less, this is the idea of the project, and I leave all my colleagues and partners of the project to explain in more details all the technical part. That's it from my side. Thank you.
Thank you, Alessandro. That was a great overview of the project. Does anybody have any questions to Alessandro? Okay, I have one general question here. What is the actual difference or advantage of our approach in this project with compared to whatever is out there right now?
Okay, let's say that I'm not an expert of 5G. I'm more expert from a robot side, but said from a robot side, we know that nowadays with the complex environment as the one that I presented right now, we need more robots and we need a better communication, because we cannot run everything inside the robots. We cannot, the robot has to communicate among them, has to communicate with a remote person, maybe, especially nowadays with the COVID. So all of this about communication, about more computational power, we have to take from internet service, network services, and as I said, also with the cloud services. And to improve this, nowadays with the current network, it's not possible to have such a quality to use this kind of services. So we try to include the 5G services because they bring more quality in the bandwidth, more quality in also in the monitoring of the services, to try to see if this can help and improve the robot autonomy.
Okay. Anybody has any other question? Okay, one more question from me then. You said that not everything can be run by the robot. Why is that?
Because nowadays with all this machine learning, artificial intelligence, there are a lot of algorithms that needs to run inside the robot, where the robot works together with humans, works in complex environment. So they require a lot of computational power. And to do this, you will need to put a lot of CPUs, even more GPUs inside the robot. This will increase the cost from one side, will increase also the thermal, let's say, effort inside the robot that has to be taken into account. So you need maybe a bigger robot, you need to take into account to thermal effect. So there are a lot of reasons that maybe can overcome using some networking internet services.
Okay, thank you, Alessandro. Are there any other questions, or shall we move to the next presentation? Okay, I don't see any other questions. So thank you, Alessandro, very much for the nice overview of the project.
Thank you, Marius.
So the next presentation is entitled Visual SLAM Resource Optimization with Docker, and that is coming from Bartosz Bratus from the University of Bedfordshire. Hi, Bartosz. Nice to see you. Please.
Hello, everyone. Just a second. Please let me know if you can see my screen.
Yes, we can.
Hello, welcome. As previously mentioned, the topic of today's presentation is Visual SLAM resource optimization with Docker. However, the optimization of the Visual SLAM algorithms is a really advanced programming topic, and today we'll focus on the optimization on the user side. How can we quickly compare and benchmark multiple algorithms on our current setup and choose the one that best fits the needs of an end user? So every single one of us that has ever installed Visual SLAM algorithm on a virtual machine or the normal computer knows that without some scripts, doing this task manually takes a lot of time. And testing multiple algorithms takes a vast amount of time. If something goes wrong with installing multiple algorithms on the same machine, there can be conflicts between packages that are used, that are shared between those frameworks. So, is there a way to test those algorithms in an automated manner without leaving, let's say, a single application or script? What would be the key functionality of this kind of an application? The key functionality would be to benchmark the first efficiency and functionality of those algorithms and compare them between each other in a similar environment. The other part would be to compare them between each other, but in the context of choosing the best one that fits the current setup. It can be a robot, it can be a normal PC, a laptop, whatever. The third aspect is time. Time is really valuable resource for any single one of us, and spending time on manual installation of each of the algorithms is, in my opinion, and some possibly would agree, this time can be a better resource to other things. So how can all those things be achieved? What this program would need to have this functionality? First of all, the program itself should have a minimal requirements, so to running up this program would take as less time as possible. The second part is the automated process. We should take the load of the user to allow them to focus on more important things to focus on the algorithm itself, how it works, and then on the IT side of things like installation of these algorithms. The third check is the live progress of the application and the algorithm, how it performs, what it does, and in the selected environment, and so on. Lastly, we would want to compare the results of the different algorithms between each other, how they performed, how much they loaded our current setup, and then possibly get some recommendations about the system. So, is there anything like this? Yes, it actually is. We have something that is called vBench SLAM, and it is the application that allows us to easily choose the dataset, compare it, and run it on the multiple algorithms while testing the execution of the program, and later on compare it against other Visual SLAM frameworks. The workflow of the application is very simple. The user has to provide a dataset in a Kitty format, but the user has to provide own dataset. It is because we want to make sure that the benchmark environment is as close as possible to the production environment. Later on, user selects the algorithm from the available algorithms that vBench SLAM is supporting. User runs the algorithm, later on opens the page with the results and can compare them to the previous runs of the different algorithms. How this application is built, you may ask. Well, for the user interface and the communication with the Docker API, we use .NET in the version 5, and the key technology that is used here is a Docker, as mentioned in the title. What we use with a Docker is we pack the image inside of the I'm sorry, we pack the Visual SLAM algorithm inside of a Docker image and then upload it to the cloud repository. When the end user that wants to test the selected algorithm chooses to run, let's say, one algorithm, the image is automatically downloaded and run on the local machine. The third technology that is used is Tangling Viewer to enable live preview of the work that is being done by the Visual SLAM framework. There are two requirements for the application itself. The first is a Docker installed on the local machine, and the second one is, for now, NVIDIA GPU, because all the frameworks that are supported by the VBench SLAM do require an NVIDIA GPU. And as it follows, we need an NVIDIA Container Toolkit to be able to access NVIDIA GPU from inside of a Docker. So let me give you a quick showcase of this application and how it can perform. As you can see over here, we've got a main window of the VBench SLAM application. We can select a data set. I have already provided it. Dataset type, for now it is only available Kitty, and selected framework. For now we have only two, but there will be more in the future, definitely. For the testing purposes, I'll choose the OpenVSLAM, and benchmark result path is the outputted map that is created by the framework. So let's run the mapping process, and in a few seconds we should see the classical Visual SLAM mapping image that we usually see. Let me adjust the camera, and as you probably see on the left window is the currently processed image with the mapped keyframes, key points, and on the right we have a map that is being created live with the option to take a look from the multiple angles on the map and so on. We can also manipulate the algorithm by pausing it, turning off the mapping process or the looping detection. When the algorithm finishes running, the program parses the map and calculates the resource usages that was used during the run of this application. We can see it by pressing the show run statistics, and right now it shows the runs of the previous run that I have made for presentation purposes. As you can see, we have two charts with that showcase the memory usage, CPU usage, and GPU usage. Also below, we have calculated averages alongside with informations retrieved from the map, like mapped keyframes, key points, landmarks, and a framework that was used. Also at the beginning, at the green color, you can see some basic recommendations about the system. I have a really powerful computer right now, so it shows all green. But later on, it can be compared to the previous runs when we press the load previous statistics. For now, for the testing purposes, it showcases all the previous runs that have been took place before. So what this application actually does, it allows us to quickly compare and check how the algorithms perform in the selected environments, in the production environments, and compare how they acted in the selected environment between each other, and also to choose the one that suits the best in the current setup that it was run on. It also saves us a lot of time, as we know time is a valuable thing. So it saves us the time on testing those algorithms. That's all. Thank you very much.
Okay, thank you, Bartosz. That was really interesting. Completely outside of my field, but it's really interesting. Does anybody have any questions? Okay, guys. Hi, Rexy.
Hello, hiya. Sorry I'm late. Just finished my lecture.
That's fine.
Thank you. Hello.
Hello. It's very interesting presentation. I might have one question. Could I ask over here?
Yes, of course.
Yeah. So in terms of building up the benchmark applications using containers, what do you think would be the advantage in terms of the deployment of the algorithm using the container and using different kind of cloud native techniques over here? So what do you actually see? Because currently we don't really use that in our robot with container, everything give us new feasibilities. What do you see in the future in terms of deployment, this kind of new infrastructure, new technology will bring to us?
What it can give us is, of course, how quick we can deploy the images to the robot, and advantages of this manner. How quick can it be? How can it be coordinated? How can sorry, Alex, I lost my thought. What benefits it gives to us? This application allows us to quickly compare the results of the multiple algorithms, and later on to quickly decide, okay, we want this algorithm to be run on every single robot of this kind, and then we can easily change the image that is deployed to the robot. I would say that this is
it's much more convenient in terms of deployment. Thank you very much.
Okay, we have one more question from, I'm not sure how to pronounce the name. It's Milan or Milan?
Yes, Milan.
Okay, Milan.
My name is Milan. Yes, I'm a researcher who works at I3M. Just to shortly in Carlos III in Madrid to introduce myself, that I've been working with SLAM recently. And I want just to, sorry, because I missed the first part of the presentation. First of all, can I find the slide somewhere of this presentation? Are they going to be available?
I'll send the link in the chat if there's here to the application later on, okay?
Perfect. And this tool that you were presenting, I guess it's available, it's open source and can be installed.
Yes, it is. I'll also send the link to this.
Perfect. Thank you very much. A question that I have to ask regarding the SLAM is, I mean, I guess that this depends on the algorithm that you try to run.
Yes, that's correct.
Does some of the algorithms that you've tested and are running are supporting simultaneous localization and mapping from two different sources, let's say from two robots? So if you have two robots that are discovering different part of the environment and then they build the same map together, is this possible, or so far it's only supported like this, let's say one-to-one mapping, where one robot is discovering and he's creating the whole map?
I will say that I'm not an expert on Visual SLAM. From what I know and from what I studied those algorithms that are tested in this application, I have no information about it, but I would need to get a much more detailed look in the algorithm itself to see if it is possible.
Okay, and thank you very much. And in terms of the data that they require to run, it's a video stream from a camera, right? Are there any specific requirements that are like minimum requirements in order to run them, speaking strictly from the source of the data? Like what kind of data is required?
Speaking about the data, just give me a second because I've got the list of all the files needed that were used to run this application. The dataset itself is in a Kitty format, so we have image sequences and then calibration times files. Also, for this, actually for the Open VSLAM, we've got configuration files for the camera and vocabulary file in DB02 format.
Okay, thank you very much. Are these also samples available in the Git repo that is like to run the demo, or this is just something locally that you have?
That is something locally, but it is already shared on the internet, so I can provide you a link also.
Perfect. Perfect. Thank you. Thank you very much.
Thank you.
Just quick comment on Milan's question. I sent a link. This is about multi-robot map merging, so you may find it useful. That's it.
Thank you very much for the info. I will check it. Thank you. Thanks a lot.
Excellent. Thank you, guys. We have to move to the next presentation. Thank you, Bartosz. That was a nice presentation. The next presentation is entitled Enhanced Experimentation Facility for Manufacturing, and will be presented by Stefano Tedeschi. I'm not sure if I pronounce it correctly.
No, it's fine, Marius, no word.
And Kandarp Amin from TWI. Please, go on.
Yeah. Can you see my screen?
Yes, crystal clear.
Okay, so good afternoon to everyone. Basically, as a TWI, myself and Kandarp, we are part of this research organization that is called the Welding Institute based in Cambridge. We take a part of this 5G project for one of the, let's say, like end user case study, especially the one in detail, let's say the one in manufacturing. This is indeed like work package 8 of this project that we run for 3 years, so the next year as well. And there are several contributors that will take a part on this work package 8. So there is a robotic that will be working almost on the part of the robot side, CAL-TEK in charge for building the virtual environment and the digital environment. Neck and Bedford that will help us to just building the orchestration with the OSM. Just a few words on the organization when myself and Kandarp work. Basically, the TWI is a member research and technology organization that has been established in 1946. We are expert on joining technology for any type of material and non-destructive testing, and there are several branches in UK and a few even outside. So over the board, and the main one where at the moment myself and Kandarp work is based in Cambridge is the one that you can see in the photo. Just come back on the work package 8. TWI is the leader on this work package, and there are different contributors as I mentioned before. The aim for this case study or this demonstrator that will be take place at TWI is to building a flexible and robust manufacturing cell for a small medium enterprise. How we're gonna do it this? So we're gonna develop an interface between the ROS industrial and one of the industrial production cell. In our case, as industrial production cell, we identify the bracing cell, one of the technology that at the moment needs more support, especially with the involvement of robot technology. The duration of this work package starts in month 22 and it will end up at the end of the project in month 35. There are 3 different tasks. At the moment, the team is involved on 2 of the first one, 8.1, 8.2. The 8.1 basically is to create the, let's say, all the characteristic to find all the requirements for building this demo from the hardware software communication point of view, and the task 8.2 that will be to building this net application for the 5G enhanced manufacturing. There are 2 deliverables that will be the outcome of this work package. One will be the final demonstrator of the TWI, and the second one will be a report that will be leader from that robotic. At the current stage, the task 8.1 prepare, as I mentioned before, the test bed. So everything that is included in the hardware, in software, any kind of like security in terms of communication and data transfer, and especially everything needs to be reported in terms of data flow diagram and architecture for have a good understanding of what we are doing. At the moment, the system, we have, let's say that in terms of hardware, almost all the hardware has been taken on place that take on board. So we have this industrial robot that more than industrial robot is a research robot, so it's a cobot solution. We just purchased even a laser scanner and a vision system, and we have even like a collision path camera that will be sitting on top of the robot. In terms of condition, so initially when we started digging around for this work package 8, because there was a need to use like a robot to support support the human operation, we established to just go for a cobot solution. Different type of cobot solution has been mentioned in the literature. The one that it was more let's say like set it for this work package, especially for this technology that is the bracing one, was using like the sequential one. So robot and human, they will just follow a sequential of step that later on you will just see in the slide. The current architecture looks like that. So there are 3 facilities, two in England, one in Italy. In the two in England are TWI Robotics, that they share the same controller, that is the OpenStack cloud. And then we have another one that is overseas, that is in Italy, CAL-TEK. All of that, they're gonna, just as I mentioned before, CAL-TEK will be involved on the building the digital environment, a robotic to just work around the communication and control the robot. It will be managed with an open source manual that will be managed by Bedfordshire and NEC. The overall architecture today, it looks like that. So on a green dot box that is on the right, you can see the net application that is working well at the moment. Is in charge CAL-TEK and is keen to develop this digital twin for 2 specific applications that we will talk later. And on the left hand side, this is all the hardware and communication software part involved. So there is the vacuum furnace engineering system, that is the system that is sitting at TWI. There is operator workpiece and jig that are the clamp method for fix the sample on it. Then we're gonna just include an headset, an X-Reality or mixed reality headset that will be wear from the operator. On the robot side, it will be equipped. We have identified Novo Robot as a cobot. This Novo Robot will be equipped with a gripper for a syringe, laser scanner, and it will be even equipped with a tip camera D415, that is a collision path. All of this will be managed through an edge application locally, send it to a 5G router, and then just communicate with the digital environment, the digital twin environment for running simulation. As I mentioned before, we select like a sequential way to work with the operator. So the robot will work in sequential way. There is a list of, let's say, like step that we have identified. We have just described it indeed. And after that, we just come out with 2 different applications. So one, it will involve an operator working on site and just make a check, let's say, like on a quality control and even support and work together with the robot for phases that you will see later in the presentation, and Kandarp will just explain that is like pre-process and post-process. And another one is on remote. So it's an offsite operator that will be guided through a remote application for help it to just run operation. Okay, I'll just move on to Kandarp now, and he can just introduce in detail what is the bracing side.
Hi, good afternoon, everyone. I hope you can all hear me. Thank you, Stefano, for passing over. The image you're seeing at the moment is our vacuum furnace setup in Cambridge. The idea will be to create a demonstrator based around this technology, and this will be supported through our partners, HAL Robotics and CAL-TEK. So this will allow us to create a demonstrator whereby we're using a robot to prepare parts to put into this furnace that you're seeing in the image. Next slide, please. So this gives you a brief understanding of what we're looking to do. So brazing at the moment, so brazing, if you're not familiar with it, it's quite similar to it's a joining process, quite similar to welding. It's quite a manual process at the moment, and hence the need for this project, for this industrial joining technique. The idea will be the robot will work alongside an operator and take over much of the manual tasks, such as applying the braze paste and performing scans. So there'll be a pre-process stage whereby the robot will apply the braze paste, take scans of the paste and also the parts for quality assurance. The parts will then be loaded into the furnace by the operator, and then the operator will unload after this process and pass back to the robot for quality inspection using the laser scanners. So that is the idea of the project. Within this, as I mentioned before, the pre-process and post-process, we'll be creating samples which will be inspected by the robot. So we're inspecting for defects, whether that be from within the part itself or in the application of the braze paste. So these are the two things we'll be investigating, but also providing quantitative data such as the volume of paste applied. So this is then captured and kept as a track record for the parts. The paste itself will be applied through a pneumatic syringe, which will also be controlled by the robot. And for example, in sample one that Stefano is highlighting here, the robot will pass around the interface of the yellow and green parts, applying the braze paste. During this process, a laser scanner will be attached on the reverse side, scanning the applied paste, giving live feedback to the operator on exactly how much paste has been applied, if there's consistency, and if there's any defects which may require rework. After the brazing process, we will then look to check for porosity or any areas which have missed braze, or if there's any overrun of braze on the parts. So this will all be conducted by the robot and providing information to the operator, freeing the operator from actually being the one doing these tasks. And then within that, we'll be embedding a quality acceptance criteria whereby the operator can review the data provided by the robot and accept or reject the parts. So we've got two samples we're looking at in these projects, one being two parts joined together, and a second sample which will have a groove of a shape, which could be the 5G era logo or something which everyone recognizes, such as a Nürburgring, and the robot will follow a complex path. So these are the types of runs we're hoping to do. For the offsite operator, the case for this is the operations will be very similar as before, but the idea changes. So this could be a experienced staff working from home, providing some teaching and on-site support whilst working remotely to a operator. But also we can look at it from the angle of a client such as Rolls-Royce, for example, in this case, could remote access in to our facilities and see exactly what we're doing, provide guidance and support and acceptance of rejection of parts whilst being remote. So that's another case study that we're looking at in this project. And just to finish off, this is just a quick visualization of what we have planned on site. So the area that you're seeing in the cage is going to be the robot cell. This is where we'll be carrying out some of the preparation activities, the pre-process and post-process activities on site. And the blue item you're seeing on the image as well is the furnace. So this is our setup on site in Cambridge for the demonstration.
That at the moment has even changed.
Yes.
But I think that is all, yeah? Yes.
Yes, that's all from us.
Excellent. Thank you, guys. Thank you, both of you, for the nice presentation. Does anybody have any questions from the audience? Okay, I have one question. Why do you need this automation and you're trying to eventually use the robot to do the work, but at the same time you want to take this at home, so someone from outside the facility can actually see what you guys are doing. What's the benefit in that? I mean, what are you trying to? What is your end goal? Let's put it this way.
Kandarp, you want to answer to that?
Sure. So, for example, brazing is just an example here. This technology can really be applied anywhere in a manufacturing site, but we're choosing brazing as the guinea pig here. The benefit of someone remote accessing in, well, there's two. One could be someone who's relatively new to the job and being trained whilst someone could be anywhere in the world. So this provides support both from Cambridge, or where we're located in Cambridge, but the idea could be TWA experts can remote access anywhere in the world that has this facility and provide on-site support whilst not actually having to be present. From a customer point of view, it provides a very close relation where they can actually support prior, because one thing about these joining technologies is once it's all set up and in the furnace, if the setup was wrong, you could be costing hundreds of thousands of pounds of damage. So this gives a client who might have a very, very expensive part that's going into a furnace, a very close contact with the parts and be with the people on site step by step and accept and reject parts before they go in, where after that process, nothing can be done after that. So that's just one example, really.
Okay, thank you. That pretty much answers my question. Does anybody else have any questions?
Marius, let me just add something. So basically, the decision to just use like a cobot, so just like support an operator, or in the future even like in the opposite way, so the human that will support the robot, is because most of the time, especially in this case for brazing, we just see that there are so many errors come out from an operator. So manual operator makes so many errors that sometimes it can just cost a lot of money, like Kandarp has mentioned. And we hope that with the use of this robot that it can support at least like the pre-phase of inspection and even like the pre-phase of release, let's say like no release, but at least like fill the gap with the paste. We could reduce this kind of like tons of error that we have in terms of quality. The second aspect regarding like the virtual environment, apart to what Kandarp has just mentioned, thinking that most of the time in TWA we are calling from member to just go there and help them to install new machine, to just run a test for them, factory acceptance criteria, site acceptance test. And we believe that using like digital environment could help them, could help us and customer to save money in terms of like integration, installation of new machine in their own site. So this is even the other reason, because we have the double part in here. So the cobot and the virtual site. Plus the use of this 5G era, the idea to communicate with the several branches around the world at the same time and share together different bits of service is something that we are keen to do.
Okay, thank you. I think Rexy has a question.
Okay, thank you very much for your presentation, and it's very interesting potentials come out. My question is, there are many technical challenges in front of you guys. And among them, which one do you think is the most critical one, faced by yourself in this development?
Kandarp, you want to answer for you, and then I give answer for me. For me, it's more on the network anyway. I'm going to answer straight away and say, at the moment, the big challenge is to integrate the 5G network. So we have a test bed running at TWI that obviously, for security reason, it doesn't run on the TWI domain. It's completely like a mobile private network. And most of the time for us, the difficult, let's say like that, especially in a company or organization like us, is to integrate let's say new infrastructure, new network, and just integrate even like machine and protocol around. So for me, it's more on the network side. For Kandarp, I don't know which one you think should be it could be like the challenge for this.
I'm not sure if it probably will be a challenge, but the most exciting one for me is the integration of the HoloLens and providing the AR support for an operator. I think that will be a challenge because there's a lot we can do, and there'll be a lot that we'll be learning in this project. But I think that's going to be a very exciting step for us.
Excellent, thank you guys. Does anybody else have any questions? I have one minor question. I don't know if I might sound stupid, but I'm curious, why do you want to use 5G for this? What's the benefit of using 5G for this?
Well, let's start from the idea that probably we will be able to collect the data in real time. And because most of the time we're looking for monitoring in process, we believe that with the 5G, we should be able to, just have a feedback in as soon as we can and just try to change the parameter of in-process technology for just make the changing and avoid any quality defect.
Okay, yeah. Maybe that was a stupid question. Anyway, thank you.
No worries. Thank you, Marius. Thank you, everyone.
Thank you very much for the presentation. We can now move on to the next one. The next presentation is entitled Leveraging a Distributed ROS to Enhance Industrial Robotic Applications, and it comes from Sebastian Andraos from HAL Robotics. Sebastian, please go on.
Hi, everyone. My name is Sebastian Andraos. I'm one of the co-founders at HAL Robotics. Very, very briefly, because I've been asked to be brief around the whole presentation anyway. HAL Robotics are a robotic software company based in London and Paris. And we create software to model, program, simulate, and control and communicate with applications involving industrial machines across a seriously wide variety of industries and fields. So our role in the 5G era project and what I'm talking to you about today, particularly in terms of leveraging ROS to improve industrial applications, I think is quite nicely demonstrated with this very abstract looking part here. This is a simplification of a boot component apologies, that automotive facilities create a lot of. They're basically the thing that sits in your boot of your car that stops your stuff falling out onto the road. And they're generally injection molded or some kind of mass produced piece of plastic covered then in some fabric. But the reality is that this kind of bucket part on the bottom here is often common between multiple types of vehicle, and it's only these connection points which are unique. So the question then becomes, can you actually create this part that is common and therefore actually does need to be mass produced with a very viable, cheap mass production process like injection molding, and then add to that in some way the unique parts for each particular model that you may have, be that through some sort of additive manufacturing process or even producing those separately and sticking them on. The result is the same. And so if we take that process as kind of a very again, I'm oversimplifying massively on purpose here. We would take the part that's input, we'd scan it, filter out some points, generate some meshes. Take the part, scan it, filter the points that are actually points of interest. Use those to regenerate some geometry. Check that against the part that we're doing, that we're supposed to have. Calculate the difference between what we've got, what we need to have, and then regenerate a toolpath for that. If we're doing that in an industrial application, the architecture looks vaguely like this, or actually could look like this. The reality is it doesn't these days, but that's what we're hoping to change. So we have at the top here, we have our robot with its controller and its tooling, so some sensors and the actual extruder end effector that we've got there. And then right at the bottom here, we have basically algorithms that need to run. And the reality is that these are all can be made very independent. Each of these could be a separate microservice, for example. And actually, in reality, a lot of these are things that already exist in ROS. And that's really the whole, well, one of the reasons that we're so interested in this project is there is a lot of interesting functionality for industrial robotics in ROS that for one reason or another is currently inaccessible. So our real hope is to be able to pull in that intelligence that the ROS community has provided into industrial applications. Then in the middle of this, architecture diagram, we have this coordinator application, which is basically sending messages from one microservice to another and eventually running things through the robot to execute. So as I said, this is a gross oversimplification, as were the previous diagrams. The reality is, when we look at the kind of more complete architecture diagram for even the process that Kandarp and Stefano were talking about a minute ago, it looks a lot more like that. Again, it's still a simplification, but it's a little more complete. So at the top here we have our manipulator, its controller. We still have that coordinator application, the tooling, and the sensors that are all part of that. And then lower down, we still have all these microservices or ROS nodes at the end of the day that we want to call into to ask to do some work for us. Where this starts to differ from the kind of simplification and what we're adding now through this 5G project is this aspect of a digital twin, which here will act as effectively as a database storing all of the sensor data that's come through, and provides a homogeneous interface for everything to query that data. So because we're obviously talking about ROS, we want to be ROS compatible. The interface to that digital twin there will be a ROS based interface to that, and by ROS based I mean ROS type messages will be understood and retransmitted, and we're also using that ROS protocol as a means of communicating between all of these different microservices, which are on our distributed network. The other part of this is slightly unique, and what I believe one of the main reasons that we can't really get away with doing this today is up in this top right hand corner of the diagram, where we're actually faced with a whole load of sensors that communicate in all sorts of different protocols. Some are talking in proprietary protocols, so very manufacturer specific protocols. They give you a big table of bytecodes and what they exactly mean, how to interpret messages in bits and bytes. And other sensors will talk in field bus protocols, so things like Profinets, EtherCAT, industrial standards, basically. But there's no, despite them being industrial standards, there is no standard. And that's that becomes a real problem. So one of our big contributions to this are these publishers on the far right hand side, and these are effectively edge applications that are going to translate local industrial protocols into ROS centric messages, which can then be fed back along to the digital twin and then queried by all of those microservices and ROS nodes that we took a look at earlier. So we're a little early in the project to have anything very solid to show you, but I did want to show briefly what happens in these translation layers. So this is a demo from a slightly different application, but it amounts to the same thing. So we have some sort of a robot, in this case it's a Kawasaki robot, that doesn't communicate in any standard protocols. Talking to it at all, in fact, over the network is complicated enough. That then gets interpreted by one of these edge devices, the translators I mentioned a moment ago, and then we can redistribute that in any format we want to. So that can be through our ROS messages, as we were doing in 5G era, or through other standard message types like MQTT or OPC UA. And then other people can subscribe to those messages and interpret them as they will. So in this example, we'll just look at MQTT and OPC UA. But again, the same thing stands for ROS as well. So apologies for the mess of the screenshot, but unfortunately there's so much going on. It's a bit of a necessity. So on the far left hand side here, we have a simulation of a robot, in this case through Kawasaki's own software. On the far right hand side, we have this edge device which is connecting to the robot, connecting to the MQTT client, and then connecting to OPC UA, so it can effectively act as that relay. And then because MQTT is a little bit complicated, we also have an MQTT broker in the middle before it transmits to the client. And down here, right at the bottom, we have our MQTT client receiving joint positions and TCP positions for the robot, and in the middle our OPC UA client, which we can see there is receiving position XYZ and a quaternion for rotation of the TCP as we move through the process. So as we can see, the robot's doing its rounds. We've got all these messages being streamed across, taken in by this edge service and redistributed wherever they need to be, even though this industrial robot is not inherently compatible with any of those protocols. And so this is what we're trying to add as well here is the ability for these industrial applications, these industrial machines, to also communicate through ROS protocols. So that's an overview, a very brief overview of the architecture. And this section at the bottom, digital twin clients, which I haven't got around to, is, I expect, the subject of our next talk by Francesco at CAL-TEK. So I will leave that up to him. Thank you very much. If there are any questions, please don't hesitate.
Excellent. Thank you, Sebastian. It was a great presentation. Seems too complicated for most of us. Does anybody have any questions? Okay, then I'll ask mine. Oh, there's one question now. Yeah, Milan, go on, please.
Hi, it's Milan. So very interesting presentation, and basically it's kind of in line with my research that I'm doing. So from industrial point of view, something that I'm curious to know about the status today of how realistic it is. I mean, this concept of microservices and dividing the robot functionalities into microservices, most probably later on virtualizing them and placing them in the robot and distributing them into a external computing device, like let's say edge device or a cloud computing device. I mean, is this something that is reality in the industry today, and offloading of, let's say, some kind of time sensitive computation? Because let's say that 5G can bring to the industry this time sensitivity, or it's far away from reality in the real industry today?
So reality today, definitely not. I mean, the technology itself is still getting there anyway. So no, the industry is always a little bit slower on the uptake. That said, we are currently running projects with automotive companies, with all sorts of steel welding companies, and quite a few other industrial projects where this same principle is being applied. So I think it will be accepted. There's kind of an acceptance of cloud now being taken in the IT space of all these companies, and I think the OT side will start to move eventually. I mean, at least our approach is to target the non-critical side first. So that's things like the data analysis. So feed all that data that's coming off the production line into something else that can then send off its whole data packet to a service running in the cloud or wherever it needs to be to have that compute performance. and do that processing there, rather than trying to change the way that the production line actually executes at the moment. And then once that's kind of become accepted and normalized, at least within a particular company, then you can start to think about bringing in that kind of those more advanced IT features into the actual production process as well. That's my theory anyway.
Yeah, thank you very much.
All right.
Excellent. I think we should move on to the demo. Thank you very much, Sebastian, for the nice presentation. I don't think the next presentation is entitled A Netapp Digital Twin Application for On-Site Smart Operator in Manufacturing Systems, and will be given by Francesco Longo and Vittorio Solina from CAL-TEK. Thank you, guys. Please go on.
Thanks a lot. Hope you can see my screen. We will keep the presentation pretty short, brief, and we will try to make a demonstration. Here with me there is also Vittorio and Luca. They will run the demonstration. I will give you just some details before the presentation. We are also, as CAL-TEK, we are also part of the 5G era project. In particular, we are included in the work package 3, the task 3.1, that is virtual reality toolbox for vertical applications. And today, I will say something more about what we are doing in the project, but we will make the demo of one of the two applications that we are developing as part of task 3.1, and that in some way were already mentioned during the presentation of Stefano and Kandarp. They have talked about on-site operators, so the operator that stay within the manufacturing cell doing something, working in the manufacturing cell, and the operator that is connected in some way remotely to make some additional things. So our digital twin, because the idea behind our work within the 5G era project is to develop a digital twin as part of the testbed in Industry 4.0. So this is the vertical domain, our application. And we are going to use not only virtual reality, but more in general extended reality. So we are going to use virtual reality from one side and mixed reality from the other side. And in particular, as I was mentioning, we are going to develop two different net application. One by using virtual reality, virtually immersive and interactive reality that will be used by the off-site operator, and another application that will use mixed reality and will be used by the on-site operator. Obviously, these two applications will be fed by using the 5G and the 5G middleware developing within the entire project, as we have listened in previous presentation, above all at the beginning of the session. So just to give you a brief description of these two applications, for the off-site operator, it's kind of digital twin, it's kind of mirror, let me say, in which we are going to receive real-time data from the real asset, the robot, the machine, the operator, within this virtual and immersive and interactive environment. And the operator will use a wearable device, such as, for instance, the HTC Vive or the Oculus, and he will be able to receive all this information and data, both real-time data and even persistent data within the virtual environment. So basically, we will have a digital mirror of the real environment. We can check what robot is doing, we can check machine status, we can check the workpiece status, we can even establish a communication between the off-site operator that is somewhere in the world in an office, let me say, and the on-site operator. From the other side, we have the on-site operator app, so the digital net app for the on-site operator. In this case, as in the previous case, we are going to receive data from real assets, but data will be available for the on-site operator by using Microsoft HoloLens. So we are talking about mixed reality, and therefore the operator will be in some way smarter because he will be able to understand better the real environment and to carry out his own operator by having suggestion, and suggestion could be of different types in mixed reality. Could be text suggestion, images, videos, or vice versa, even in interacting with the knowledge navigator, an intelligence assistant able to provide questions to the answer made by the operator. And furthermore, the operator can have a direct access to the most important information related to the machine, to the work pieces, to the robot status, and so on. Well, this is enough for the presentation because we would like to use few minutes to show you the first demonstration of the net application for the on-site operator. So we have worked on and we are still working on this application. So please consider that this is just the first demonstration that we have developed. We are still working on it. We expect to release additional, let me say, functionalities as part of this application in the next weeks, and to deliver by the end of December of this year both the on-site application and the off-site application. Now I'm going to leave the floor to Vittorio and Luca. I will ask you, Luca, to share his own screen and Vittorio to take the word. And from my side, now you will see the screen from Luca showing the mixed reality environment. And you see Luca is looking at our lab. I am here, by the way, Luca, if you look at me, you can see even myself. I am here, this side, wait a minute, I'm here. So here you will see the mixed reality environment. Vittorio will comment the application, and I will show you with my camera, if I'm able, who is wearing the, okay, from my camera, wait a second, it's the mobile camera, you should see Luca that is wearing the HoloLens, okay? So Luca is wearing the HoloLens. On the major screen, you see what Luca is going to see, so the mixed reality environment, and Vittorio is going to comment the application. Please, Vittorio and Luca.
Okay, thank you, Francesco. As mentioned by Francesco, we have two main apps, and here we are going to see the digital twin Netapp for the on-site operator. When the operator puts on the HoloLens and starts the app, she can view a set of information. As you can see below, you can see static information such as the project name or the customer name. At the top right, the project logo and the logo of our company, that is CAL-TEK. At the top left, you can see dynamic information. Please, Luca, you can zoom in. Yes, perfect. And then here you can see notifications and a drop-down menu. Luca, if you click on the icon notifications, please. If the operator clicks on the icon notifications, he can receive notifications about a certain operation or machine. Okay. Okay. While if the operator clicks on the icon menu, okay, Luca is sending
checking something, obviously. Yes. It's a demo, we said, it's checking something. So that's the Murphy law, let me say.
Yes, he's sending the notification live.
So let's wait a couple of seconds.
Yes.
So pretty normal, let me say, when you run a demonstration, it's typical that you get some okay.
Okay, and he received some notification, for instance, a result about laser scan. It's just an example. Okay. Okay, well, Luca, we can go to the icon menu. Okay, if the operator click on the menu, all the processing phases appear. For example, workpiece clean metal surface preparation, workpiece positioning, laser scanner initialization, and so on. We can try to click on the first operation, which is workpiece clean metal and surface preparation, for instance. And yes, here the operator can see another menu with different possibilities: CAD, process description, special info, then additional information about the operation. At the beginning, we can try to click on CAD, for instance. If the operator clicks on the item CAD, she can view information about the workpiece in terms of shape, size, and so on. In particular, the operator has the ability to zoom in or zoom out to acquire, for instance, additional information. Then, Luca, you can try to zoom in or zoom out. Here, we could have a DWG file or a PNG file and so on. Well, perfect. Luca, we can close this window. Perfect. If we click instead on the icon process description, the second icon, the operator can acquire additional information about the process. In this case, how to execute the process. In this case, the operator takes the workpiece, cleans it, and prepares its surface. Then the workpiece is placed on a table for the execution of the robot and laser scanner operations. Then additional information about this space, this activity. Okay, perfect. Luca, we can close this other window. Perfect. If the operator clicks on the icon Special Info, the third one, perfect. When the operator clicks on Special Info, some additional elements are activated, which appear by looking at specific points in the environment. In this particular example, we can see a green parallelepiped and an arrow that indicates to the operator the exact point in which to apply the braze path. Then this is an important help for the operator to avoid mistakes and so on. Perfect. Thank you, Luca. We can go ahead with the other item. We can click on videos, for instance. As you can imagine, if the operator clicks on the icon videos, she can see a video about the shop floor, about a video to have additional information about the shop floor, about the manufacturing environment. Here, in this case, we are watching the furnace of our project previously described by Kandarp and Stefano. Perfect. Okay, Luca, we can go ahead with the other icons. As you can imagine, if we click on photo, we can see a set of photos describing the operation. Then we can see different pictures by clicking next and previous and on this menu. Perfect. Perfect, Luca. Okay, perfect. We can go ahead with the last icon, offsite communication. Okay, perfect. When the operator clicks on offsite communication, a list of people who can be called for any type of communication appears. Here you can see a list of operator of our company CAL-TEK, and well, this is just to see that the operator can call different people for helping him, her, and so on, for communicating something and so on. Perfect. We can close also this window. Luca. Okay. Okay, perfect. And I think that the demo is finished. It's enough. This is just a first step for us, as mentioned by Professor Longo. I hope
Vittorio, let me add something. Let me add something else. So basically, you have seen the first demonstration, and you have seen, let me say, persistent data like videos, picture, or CAD files, and 3D models, and so on. There are two major points. First of all, we are now integrating real-time data coming from the robot by the bracing furnace, and so on. So pretty soon, the operator will receive real-time data within the HoloLens, and this is the first point. The second point is that the persistent data, text, videos, and images, can be created directly by the off-site operator, so the operator that is working in the office, by using a dedicated web application. So no matter where the off-site operator is, he or she can use a web app application that will allow to put information like video, text, images, and so on, that immediately becomes available for the on-site operator that is using the HoloLens. And the type of information that can be inserted are not necessarily the one related to the manufacturing processing that we have seen today. Could be general, could be related to manufacturing process, or could be related to any other process. So the architecture of the HoloLens application is general, let me say. We can use the application for the manufacturing domain, but even for any other domain, just for scalability and for demonstrate the usability of this solution even in different domains. And I feel that's all. If you have questions, we will be very glad to answer.
So thank you, guys. I was really impressive with the virtual reality. Does anybody have any questions from the audience? Okay, I have one short one. How do you guys communicate with whatever robot you have in the plant? I mean, I can understand the virtual reality, but how do you communicate that whatever you want to do to the robot itself?
That's a nice question. We have already faced this problem together with Sebastian and even Stefano. Basically, the idea is the following. From the robot side, you have ROS operating system. From the Microsoft HoloLens side, you have Unity 3D, because in our case, the application for the HoloLens has been developed by using Unity 3D. Now, there are some, let me say, bridge or protocol that are available in ROS that can be used to, they are called ROS server or something like that, if I remember well. I'm not an expert in ROS. I'm not the computer scientist guy, to be honest. But there are some libraries available that can be installed from the robot side and even from the Unity side, and these allow the communication by using actually WebSockets. So we are able to exchange information. Obviously, later on, all this data, as was mentioned by Stefano, should pass through the 5G era middleware to use the 5G network.
Okay, that explains it. Renxi has a question, please.
It's just a quick question about the deployment of the application. It's very interesting application. You demonstrated nice intuitive demonstration. And suppose this development has been completed, and then in the future we may have many workplace, many teleoperator, many people using your services at the same time. And then this deployment is expected to be done automatically and with the 5G era and kind of optimizing the resources required by your services. So my question is, from your experience now, what is the element in your demonstration which require load of resources? So for example, certain element might require networking resources, certain element might require computing resources. From your experience, what kind of resources is critical in the demonstration you have showed us?
Oh, that's a nice question. Let me think about. I feel that you may need network resources as soon as you start exchanging a lot of data that could be, for instance, data coming from machine, from multiple robots. So currently, obviously, the case study is focused just on one single manufacturing cell. But as you were mentioning, you expect in some way to have multiple manufacturing station, multiple plants, multiple machine, multiple operators doing this. So there are two critical, let me say, points. For sure, having a good network connection or speed, and that's the reason, let me say, of 5G. And from the other side, I would say that it is not the computing resource the most important part, but in order to deploy immediately this solution, what is really needed is the capability for the user, not the user staying in the on-site, but the user off-site, to define immediately all the contents needed by the mixed reality application. So, for instance, you saw during the presentation a kind of parallelepiped with an arrow. That parallelepiped is positioned in a specific place close to the machine, for instance. Now, let's suppose that you have 100 machines, and for each machine you have to define specific points, specific position, specific 3D models, and so on. You have in some way to develop a web app application that allows the user, the offsite user, to define immediately all this information, and then this information becomes available for the operator. So this is needed to, in some way, to scale this solution and to allow to deploy the solution immediately. Because for the other side, thanks to the HoloLens, you can also create a 3D mapping of the environment and understand the position of each object, and give this information back to the offsite operator that is going to put all the mixed reality contents. Could be video, text, could be 3D models, and so on. Again, I feel obviously there is a lot in terms of data to be transferred from and toward the manufacturing system, a complex manufacturing system, and that's the reasons of 5G. But from the other side, in order to deploy, you need to work on the usability and contents creation from the off-site operator side. I hope this gives a bit of explanation to your question.
Oh, thank you very much. It's very good insight. And especially you emphasize on the preparation of the resources for different kind of sites. This is going to be critical. I would assume that this would be a key research focus in the future, especially with different kind of machine learning techniques, integrating prior knowledge into the live information capture. With meta learning is getting very popular. I would assume that a lot of new algorithms would be introduced in the field, helping us build better future in the direction. Thank you very much.
Sure. Thank you for the question.
Thank you guys for the great demo and the presentation. I think this concludes our special session for the project. It was really nice to see everyone here. Thank you for contributing and joining. Unless there are any other questions from the audience, I think we can close this session. Okay, I don't see anyone else having a question. Thank you. That was perfect timing, yes.
Are we going to take a photo for the presenters today?
Yes.
They made very good.
Let's put the gallery mode.
I think everything is recorded, so.
Yes, I can download later on. Rex, if you like, I can show you I can send you the video. So let's ask to everyone to switch the camera on. Oh, we are still 6, so open your camera, don't be shy.
I need to be a little bit further to get slimmer views of myself.
Wait, we wait for Luca that is coming. Without HoloLens, obviously. Okay, I have to switch my camera on as well. Sorry. Okay, here we go. And who is going to stamp the picture?
I can try that.
Okay. Oh, so smile. Okay. Okay, we have the picture. I took one picture.
Perfect.
Excellent.
Good.
Okay, guys. We can close the session now. It was great to see you. Thank you. I'll see you soon again.
Thank you very much.
Thank
Bye.
you very much.
Thank you, guys.
Bye.
Bye.
Thank you. Bye-bye.